right, hello. All right. Well, welcome back. You guys had a nice weekend. Um or as nice as can be anyway. Um so let me start off with a couple organizational things here. Um so first thing is tonight after I record the lecture videos. So I'm going to record the lecture videos for tomorrow's lecture after class today. I'm a bit behind on that. Um, but I'll get those done after class. Hopefully, I can knock them out before office hours, but if not, I'll have them done shortly after. And then after that's done, I'm going to finish grading exam 2 and then get those scores up. Um, so that should hopefully be done by the end of the day today. Um, and then for exam 3, what we're going to do is sort of the material that we finished this week. So it'll be this stuff on the fundamental theorem of calculus, and we're gonna do the substitution rule tomorrow, U substitution. Um, Sorry, still not feeling so great. um, fuck. All right. Yeah. So tomorrow's material will be sort of the cutoff for um the exam 3. So what I'm going to do is next week I'll post these segments for the exam on Notebowl, or sorry, on WebAssign. Um, and my plan is to make them due April 14th, so you have some time to kind of work on them. But the structure, my goal for that is going to be I'll break up the topics into smaller chunks, and then I'll make like smaller segmented exams basically. That'll add up to the full exam 3 total. And it won't have like the full like 100 attempts like the homework does. It'll be something a bit less, like 10, 15. And my goal is to have it sort of take off a small percentage for each wrong answer. But then I also want to give like a baseline score. So sort of like maybe something like 20% of the credit if as long as you've tried each problem. So it'll probably be, let's say if I do 10 attempts per problem, then it'll probably be something like, each attempt takes off 8% of the points for that particular problem. And then if you use up all 10, then you just have the 20% left. Something along those lines. I want to put up like a sample of what that could look like. Hopefully I'll get that done today after the lecture videos, so you can have a little idea of what that'll look like. And they'll be timed exams or timed assignments. So like let's say, one chunk is timed for 30 minutes. So it'll be from when you open the assignment, you'll have 30 minutes to complete it. So my goal with the segmented thing is, since all of our due dates and stuff are kind of like later, um, later in the, like April 10th, I think, is the first round of dates. I figured, breaking the exam up into segments so you can kind of do piece by piece. So like if you've made it through, say, all the or like the stuff we did before spring break, all the first and second derivative test stuff, if you got that, you can do the test on that part. Then when you want to try to do the optimization problems, you can do the exam chunk on that. And I'll announce how I'm chunking up the exam. Like, I don't want it to just be random. I want you to kind of have an idea of what's going to be in each part. So hopefully that kind of helps lower the stress about what the exam will be, and sort of how all that breaks down. Gives you some time to sort of, get caught up if you need to, because sure, I mean, I know I'm very behind on life right now, basically. But I don't want to kind of rush anyone through the exam. And we'll see how that goes. So, hopefully that kind of makes sense. Before we get started with the problem set, though, there any questions? Anything? All right, let's go ahead and get started here. So problem 1, I meant to change this back to black. So problem 1, we want to find the area under the graph of this function, 2x cubed minus x squared, on the interval from 1 to 2. Okay, so in order to do this, now we could set up, the definite integral through the fundamental theorem of calculus stuff, but I want to set this one up. I want to do it with Riemann sums. Okay, and then we'll go through and do some definite integral stuff, right? And move to basically the easy way of doing it. All right, so basically I want to find this. I want to do this problem a couple times just to get the different methods out. So the first one I want to do is let's set this up by hand and see how this kind of problem would work. So sort of, let's say if we do this, let me write here by hand. Did I post the wrong thing? It should be the same problem. Did I copy it wrong? No. Did I post the wrong thing? It's very possible that I did. I know I had accidentally posted the Math 145 stuff earlier. Oh, I did it again. Let me upload the correct one. So I made the same mistake 2 times. Oh, yep, okay, I had the wrong folder open. Let's try that again. Yeah, maybe you don't want the the one that I actually did upload. That would be Math 145. Sorry. All right. It should be fixed now. All right. I'll give you give you guys a second to pull up the new one, which is the Math 135 one. Thank you for pointing that out, by the way. Wouldn't have noticed. All right. So now that we got that sorted, go ahead and do this. So yeah, so we're trying to find the area under this graph from 1 to 2. So I want to do this by hand first. Right? And when we do this by hand, basically what we're saying is we want to compute this area as the limit of the Riemann sum. So we want to compute this here, where we can use left endpoints, right endpoints, midpoints. I think it's always best to just use right endpoint here because it looks a lot better. Or it's a lot simpler, the delta x's. All right. So I was also looking in the book. I think they use ci instead of xi star. I'll leave that up to you, whatever you guys think looks best. Anyway, so we need to compute all these pieces. And I guess I should point out, this here, this is f of x, of course. So let's compute these things. The first thing we need is delta x, which is always b minus a over n. Now, when we're doing the actual exact area, we want to leave n as n. We don't want to plug in any number for it. We're just going to have 2 minus 1 over n. There's our delta x. One of these days I'll stop hitting that zoom button. Okay, xi star. Right, since again the right endpoints are going to be the easiest thing to use, we're going to use a plus I delta x. So this is going to be 1 plus I over n. Right? And then we need f of xi star. So this is 2 times 1 plus I over n cubed minus 1 plus I over n squared. Okay. So we need to expand this out. So this is going to be 2 times, when you cube something out, you can use that Pascal's triangle to figure out the rules. So this is actually going to be 1 plus 3 I squared over n squared plus 3 I over n plus, oh sorry, I did this backwards. It was in the other way. I squared over n squared, and then I cubed. All right, so you start by sort of taking this thing to 0 power, 1 power, 2 power, 3 power, and then take this entry and start on the right side, 0th power, 1st, 2nd, 3rd power. And then the coefficients are 1, 3, 3, 1. Of course, you could always use Mathematica to do that computation or sort of foil it out piece by piece. Here, 2I over n plus I squared over n squared. Right. So now we want to, simplify what we can. So here we have 2 plus 6I over n plus 6I squared over n squared plus 2I cubed over n cubed minus 1 minus 2I over n minus I squared over n squared. I'm deliberately writing the numbers out front like this. I actually should have factored out the n's with them. That was a bit unintended here. So let's see, 2 minus 1 gives me 1. Now let's look for these ones. The ones with just an I in it are these. So that's going to give me plus, I actually want to write this as 4 over n times I. Sorry, like I said, I meant to factor out the n's with the number. Okay, so there's that part. Now let's look at the n squareds. These are the I squared, sorry. So those are going to combine to 5 over n squared times I squared. And then there's only one cube term here, plus 2 over cubed, I cubed. All right, so that's f of xi star. Bit of a mess, yeah, but we'll make it through. So what we then need to do now is the actual area. This is going to be the limit as n goes to infinity. So I'm just going to rewrite this sum real quick. Sum from 1 to n, f of x star to x. All right, so let's plug in what we have. Limit as n goes to infinity of the sum I equals 1 to n of all this stuff times, let's see, what was delta x? 1 over n. At least that part's nice. Okay. So now what I want to do is I'm going to distribute this out, and then I'm going to break up the sum over each piece here and factor out everything that's not an I. So just to combine some steps together here. So first we have just the constant part, which I'll leave like this, plus, right? I can factor out this 4 over n, and then I have sum from I equals 1 to n of just an I. Okay. Now I'm going to do the same thing for this part. So it's almost like I'm distributing this sigma from I equals 1 to n over each part of this. That's sort of not exactly what it is, but it functions in that exact same way. Oh, sorry, I forgot to multiply in this. It's supposed to be... Sorry, I totally forgot a step. This is 1 over n times 1. I have to multiply this in. So this one's supposed to be n squared there. Sorry. Yeah, so I'm sort of distributing this sigma and factoring out all the stuff that's not an I. So here, I multiply the 1 over n times the 5 over n squared. Gives me 5 over n cubed. And then I have my sigma of I squared. And then lastly, multiply this over here. 2 over n to the 4th. I equals 1 to n of I cubed. How did we calculate the change in x? So change in x, delta x here, this is b minus a over n. So this is, the interval here is always a to b. So when we compute delta x, we're just doing b minus a over n, so it's the end of the interval minus the start. That says how long the interval is. And then the over n part just says, all right, now we're cutting it into n pieces. N equal-sized pieces. That look all right? Cool. Yeah. And like I said, this stuff here, it looks complicated. It's just a bunch of algebra, really. Like I said, we're basically multiplying this 1 over n inside on each of these 4 terms. And then imagine sort of distributing the sigma to each piece. And then factoring out everything that's not an I. So that'll leave us with this. Okay. And then we use those formula. We can add up these 4 things here. There's actually the formulas we had talked about for those. We have 1 over n. Adding up I copies of n is just going to be n. Right here, we have 4 over n squared. Adding up I from 1 to n is n plus 1, 2. Right, 5 over n cubed. Should make sure I don't run out of room here. Right, when I add up I squared, this is the kind of weird, complicated one. n plus 1, 2n plus 1, all this over 6. All right, I'm gonna run out of room, so let me move stuff down a bit. And then finally, 2 over n to the 4th times this one. The one for I cubed is actually quite nice. Sorry about that. That's why I don't have camera on today. I'm still not feeling great. Yeah. So the one for I cubed, we just take the one for I and we square it. N squared, n plus 1 squared, 4. All right, so now there's no more sums. Now it's just we need to do some limits. So it could help if you want to simplify things a little bit. Like here, we can simplify this to a 1. Here, you can multiply this out if you want. I won't bother, actually. But I will simplify what we can. What we can simplify easily. Here. This will be 5. All right, nothing really simplified here. And here, we do get a little bit of simplification. This n squared and n to the 4th, that 2 and the 4, simplify down to the... Right. So now when we're doing this limit, we're just going to use sort of our knowledge of how limits to infinity work, right? If we have a polynomial on the top and a polynomial on the bottom, if they're the same degree, then we just take ratios of the leading coefficients, right? The coefficients of the highest power. So here, well, this is just 1. Now, if we look at the top here, the highest power is going to be n squared on top and on bottom. They're both n squared. The coefficient of n squared on top is going to be 2. On the bottom is going to be 1. We get plus 2 over 1. Here, the highest thing on top is going to be an n cubed. And the way we get that is the 5n times this n times this 2n. So we have 10n cubed up top, 6n cubed on the bottom. So this is 10 over 6. Right? So it's important not to forget about this 2 right here. And then over here, we're going to have an n squared on top and a 2n squared on the bottom. Oops. So the coefficient's 1 on the top, 2 on the bottom. Right, so when we simplify this, let's say this is going to be 1 plus 2 is 3, plus 5/3 plus 1/2. So common denominator is 6. 18 plus 10, 3. So 31 over 6. So that's that answer. Right, so this is how we would work through this one by hand. Which is, you know, a bit of a long drawn out process. Again, I think it's valuable to do this at least sort of once. Just to kind of understand how this process works. So I might do something on the final exam, like having you guys write up one of these and scan it into me or something like that. But as for the exam 3, I'm not going to bother with doing, having you guys write this out. Now there are problems, and you'll see them in the homework today, I think. Sorry. That sort of say, like, here's a Riemann sum, what is the area it's computing? But as far as writing all this out, I might have you guys like write one up and send it to me for the final. All right. But since we do have Mathematica here, let's talk about how we would do this using Mathematica. Also as a good way to check your answer. Let's see. I need my sample code here. Where has it gone? The Riemann sum code. Here we go. All right, let's see if this captures the right one. That is not the right one. Let's save that. Awesome. There we go. So when we're doing this stuff with Mathematica here, right? So we're gonna set this up kind of the same way we had before. So here we have 2x cubed minus x squared. Right? The difference here is we want n to be arbitrary. So we bop that line with the n. And then here, you can change this if you want. You can use left endpoints, it'll work just fine. You can use right endpoints, since that's what we did and we want to maybe check our computation. But no matter what you do, left endpoints, right endpoints, midpoints, it's all going to boil down to the same answer. Right? So, oh, we need to fix our a and b. A is 1, b is 2. We start at 1, end at 2. Let's go ahead and run this. Okay. So, with Mathematica, we're kind of already figuring out here that the area, which is the limit, still the limit of this sum. Right, so we're still computing this thing. Mathematica simplifies it for us. Right, so it is doing all of this work that we did. It's just combining all of these together and giving us sigma immediately. Right, which we have is 8 plus 33n plus 31n squared over 6n squared. Okay. So now we can see here, you can use Mathematica, of course, to take the limit of this. So limit of this stuff is n goes to infinity. And look, there we go, 31 over 6. Which you could probably at this point already see, since the top and bottom are both degree 2, you just take the highest powers and divide them. Right, so as far as any exam or anything like that, this would be perfectly fine for you. Right. All right. Now, the last way I wanted to do this problem is sort of the whole focus of the fundamental theorem of calculus. So I'm just going to write FTOC for fundamental theorem of calculus. And this is going to make life a lot easier. That's sort of the goal of this theorem. Right? So the area, fundamental theorem of calculus tells us, well, this is the integral, right, from a to b of f of x dx. So from 1 to 2 of 2x cubed minus x squared dx. Right, whenever we're finding area, all we're doing is just computing this definite integral here. So we integrate this. When we integrate this, we're trying to find an antiderivative. So let's write down an antiderivative. Antiderivative of 2x cubed. We're looking for something whose derivative is that. That would be 1/2 x to the 4th. Right? And then minus x squared. So an antiderivative would be 1/3 x cubed. And again, we can put on the plus c. We can leave it off. It doesn't matter. Just for sort of showing why the c doesn't matter, let's go ahead and add it in here. Right, and then we're going to evaluate this from 1 to 2. Right? So let's go ahead and do this. When we evaluate this, we plug in the top number, and then we subtract, and then we plug in the bottom number. So we get 1/2 times 2 to the 4th minus 1/3 times 2 cubed plus c minus 1/2 times 1 to the 4th minus 1/3 times 1 cubed plus c. So what you can hopefully see here is we're going to get c minus c. So these cancel out. Right? And that'll happen every single time. And even if you decided to, add a specific number, no matter what you added, these two always cancel out. So there's really no reason to have the c there in the first place. But again, it wouldn't hurt anything if you did. Right? Because we can use any antiderivative we want here. It doesn't have to be a specific one. Okay, so now that we have that, let's simplify what we got here. So 1/2 of 2 to the 4th is 8. Here we have 8/3 minus 1/2 minus 1/3. So here we have, let's see, this is going to be 24 over 3. So this is 16 over 3 minus the 6th. So that's 32 minus 1 over 6, or 31 over 6. So we did the same problem 3 different ways and got the same answer, which is kind of good to know that everything we talked about sort of checks out. Doing this by hand, doing this with Mathematica, or using the fundamental theorem. So obviously in most cases you would use this fundamental theorem of calculus 1. But these other two, this one's kind of useful to say, how do we do this, conceptually? How do we build it? But then Mathematica, bypasses the hard work for us. And fundamental theorem of calculus uses neat tricks. So any questions at all on the first problem here? I know this kind of expands a bit on what the question actually says to do, but I wanted to make sure we kind of went through all 3 ways of computing that. All right. So the next problem here is just computing a bunch of definite integrals. Let's just go through the list here. 2. Number 1. Sorry about that. All right. Problem 1 here. We're doing the integral from -1 to 0 of 2x minus 1 dx. So just find an antiderivative of this piece in here. And an example is x squared minus x from -1 to 0. Plug those numbers in. So we get 0 minus 0 minus, so you plug in -1, we're going to get 1 minus -1. So this will be -2. Problem 2. I want to integrate from 1 to 4 of 8x cubed minus x. So again, we just need to find an antiderivative for this. So that'll be 2x to the 4th minus 1/2 x squared from 1 to 4. So again, all we do is just plug in the top number first. That's a big number. 256, 512. Minus 4 times 4 is 16 minus 8. Minus 2 minus 1/2. So let's see, what do we get here? This is going to be 504, 502, 502.5. So you can say 502.5, you can write it as a fraction, which would be 1005 2. Again, or 502.5, just fine. Either way. Right. next one. So here we're going from minus 8 to 8 of x to the 1/3 x. Right, again, we talked about sort of the power rule for antiderivatives, right? There's nothing sort of stopping us from doing that. So the antiderivative of this, we take this, we add 1 to the power, and we divide by that number. This is from minus 8 to 8. So this over 4/3 can be 3/4, and actually we can factor that all the way out and then just plug the 8 and the minus 8 into this. So 8 to the 4/3 power, in fact, let's write that first. The 4/3 and then minus negative 8 to the 4. Right, we sort of get this. 3/4. Now 8 to the 4/3. When we cube root 8, we get 2. And we raise it to the 4th power, we get 16. Yes. When we cube root 8, or negative 8, we get negative 2. When we raise negative 2 to the 4th power, we get 16. So this is actually just 0. Right? And this is actually an example of a bigger concept here, which is this is what's called an odd function. And we're integrating it over a symmetric interval like this, so we have to get 0. So that's something I think we'll mention again at some point. I forgot when I wanted to mention that later. But there's some neat tricks if you have even and odd. All right. Any questions so far on doing these integrals? These definite integrals? So now let's look at the slightly more complicated ones here. Well, actually, this one right here is the most complicated of them. So this here looks a bit trickier than it actually is. Right? So all it comes down to is we want to rewrite this in a way we can understand. So first thing we can do is rewrite it like this. Right? And then the next thing we can do is remember that when we're doing square roots, that's putting things to the 1/2 power. Well, actually, first let's do this. Let's split up the square root over these two pieces. Right? Remember, if you're multiplying two numbers and then doing the square root, you can square root first, then multiply. But we couldn't do this if this were like 2 minus x, something like that. Then we couldn't split the square root up over there. So here, square root 2 is just some number. In fact, it's just some number, so we can pull it all the way out of the integral. We don't even need it in there anymore. Square root of x to the minus 1/2. Again, remember, square root just means take the exponent and multiply it by 1/2. So we have x to the minus 1/2 here. And look, now it's just the power rule again. Got square root of x times x to the 1/2. Oops. Supposed to be square root of 2. Divided by 1/2 from 1 to 8. Right, so this is 2 square root of 2. That 1/2 comes out here as a 2. We have square root of 8 minus square root of 1. This is 2 root 2 times 2 root 2 minus 1. Or you can leave this as square root of 8 if you want. If you're really feeling up to it, so this would be perfectly fine. Or maybe I should do this. Just leave this as square root 8. If you're feeling quite up to it, square root of 8 is 2 square root 2. So this really is 8 minus square root 8, if you were so inclined to do that. But again, you don't have to do it. All right. Let's look at 5 here. So 5, we're now integrating from 0 to pi of sine of x minus 7 dx. So, to do this one, right, we just have to figure out, again, what are these antiderivatives? So, antiderivative of sine of x, right, would be minus cosine. Antiderivative of 7 is negative 7x. Oh, sorry, of 7 is 7x, but minus that. And then we go from 0 to pi. So plug this in, plug in pi, negative cosine of pi, minus 7 pi, minus negative cosine of 0, 0. Right? And here you'll want to remember what these values are. So cosine of pi is negative 1, so this is 1 minus 7 pi. Over here we have minus. Cosine of 0 is 1, so we have negative 1. This is going to be 2 minus 7 pi. Okay. Any question there? Let's go ahead and look at the last one in this group. Integrating from minus 1 to 1, e to the theta plus sine theta. I have sine twice. Oops. Right. So let's go ahead and compute this integral. So again, we need antiderivatives of these things. So the antiderivative of e to the theta is just e to the theta. Antiderivative of sine theta, we already saw above, minus cosine theta. And we're evaluating from minus 1 to 1. So let's plug this stuff in. We have e to the 1 minus cosine of 1. Okay, that's the first part. And minus e to the minus 1 minus cosine of negative 1. All right. So here's something. I don't know if you guys remember this from when you first learned about sine and cosine and all that. When I have cosine of a negative number, that's actually equal to cosine of the positive number. Right? So the property we used here is that cosine of minus x is equal to cosine of x. This is actually what it means for a function to be even. Kind of mentioned that earlier. And by the way, an odd function would be something like sine. Sine of minus x is just sine of x. Right, these are useful often for computing integrals, as we'll see a bit later. So it's going to turn out that these pieces just cancel. And so what we're left with is e minus 1 over e, or e minus e to the negative 1. Either way you want to write it is fine. Right, so both of these are okay. Right? So that was the last one of those. Any questions about that at all? All right. It's a nice thing about this section right here, fundamental theorem of calculus. There's a lot of theory that goes into making it true. But the nice part is if you can do antiderivatives, this stuff is basically free, which is pretty cool. To get a nice break after all the kind of intense derivative test stuff. All right. So let's go ahead and look at the last problem here, problem 3. Right. So in problem 3, we're just doing some derivatives, right? And this is using the first part of the fundamental theorem of calculus. Right. So if I have f of x is the integral from 0 to x of t squared plus 1 dt, right? Since we have just an x up here, and we have a number down here, the number is irrelevant as long as it's a number. Then, when we do the derivative, all we do is take the x and pop it in for t. Oops. We get x squared plus 1. That's it. So the integral goes away, the dt goes away, because those kind of belong together. So here, let's look at the next problem. We have the integral from x to negative 1 of t to the 4th plus dt. Before I rush into that one, any questions about this one? All right. So this one here, remember up for number 1, we said the number, the constant, had to be at the bottom, the x had to be on the top. Here, these are in the wrong order. Now we talked about a property of definite integrals though, which says we can flip the bounds at the price of adding a negative sign. Right? And remember, that was just because delta x changes sign when we swap the order. Right? So now that we're here, this is all fixed, and so f prime of x, we just keep our negative, take this x, pop it in here. Actually, I don't really need these parentheses, do I? Right? And then there we go. So just interrupt me if you have a question here. Go ahead and write out the next one. F of x is the integral from 0 to 2x of cosine, just to make sure it's clear, this is t to the 4th inside the cosine. See? Right? So when we're doing this one, this basically turns into a chain rule problem. Right? So our fundamental theorem of calculus says we can do the derivative as long as there's an x up here. But if you have something that's not an x plugged in, then it just turns into chain rule. It's not really that big of a deal. So when I do the derivative, I think of this whole integral as the outside function, and this upper bound as the inside function. And then all I have to do is just plug this in as I normally would. Cosine of 2x to the 4th, and then times the derivative of this, 2. Okay, so 2 cosine of 16x to the 4th, if you wanted to expand that out. Go. So that's it. So the definite integral stuff hopefully is pretty straightforward. Computing these derivatives of these integral functions here. These types of functions are quite useful as cumulative functions. So you'll actually see these quite a bit in physics if you do that. They can show up in probability as well. They're kind of like a, what do we call that? A cumulative probability function, I think is the correct term. So it's kind of saying, like, starting from the beginning, what is the chance that, or say we're looking at something like, pick a random number between, 1 or 0 and 10 or something. right? So if we wanted to say, like, what's the probability of picking something less than 7, we would integrate our probability density function from 0 all the way up through 7. And that would sort of add up the probabilities of everything up to that number. Just as an example. And then you might be interested in, like, all right, well, as this number that I'm trying to be less than increases, what is the rate of change of the probability? And the derivative of it of this type of function would give you that. Okay. So now that we're sort of through all the examples here, any questions anyone wanted to ask? Otherwise, I got my work cut out for me, so it will be done for the day. And I'll try and get all this stuff out to you guys as soon as I can. We'll press on tomorrow. All right, then, everyone. Thanks for coming by. Thanks for watching. And hope you guys are all doing all right and staying safe. And you and your families are doing well. Yeah, with that, take care. Have a good afternoon. I'll see you tomorrow.